The last colligative property that we're going to talk about in this course is osmotic pressure. This is much different than the others, but still works in a colligative way. So just to review or recap, what does colligative mean? That means that the properties are dependent on the amount of solute dissolved and not on the chemical identity. So just to recap, colligative properties, that means that the properties are dependent on the amount of solute added and not on the chemical identity. All right, so this picture that I stole from a textbook, actually gives an impression of what what osmotic pressure is going to look like. Now, eventually, if you have a container that you have put inside a solution, the smaller container has a semi-permeable membrane. That means that it's going to allow smaller molecules to escape or enter, and eventually, over time, you're going to have a solution, a pressure build up. So think of it this way: if I have a coffee cup, okay, so here's my coffee cup, okay, and I put some hot water inside this coffee cup, and I'm gonna, let's say, put a tea bag, okay. And so here's my tea. Now, eventually, over time, water is going to come into that tea bag. Okay. And eventually, over time, that the water is going to mix with the tea. Smaller molecules out of smaller particles from the tea should be out of the tea bag, should be coming out into the solution. Solution turns brown or green depending on what kind of tea you're drinking. So that is if we're keeping the pressure constant. Here in these figures, we're eventually, over time, pressure is increasing. So osmotic pressure exerted by this column of liquid in this tube is sufficient to prevent further net passage of solvent. So what we're seeing here in this figure is that the solute does not pass through this membrane. Semi-permeable membrane. Okay, and the solvent goes from a higher concentration to a lower concentration. Okay, now regarding the liquid raising in the tube, what force causes it to stop? Gravity. Okay, so the mathematical analysis for osmotic pressure differs from the other colligative properties in that instead of using molality or mole fraction, it's going to use molarity. Okay, because we're assuming we're at constant temperature. So the equation that we're going to use is a capital pi. Okay, so capital pi is equal to the molarity, m, times r, the universal gas constant, times T, the temperature. So let's get this. So M is going to be your molarity, which is moles per liter. R is the universal gas constant, which is going to be 0.0821 liter atmosphere over K mole. And then T is your temperature, and that's going to be measured in Kelvin. Okay, so that's how we calculate osmotic pressure. So let's try this out. What is the osmotic pressure of an intravenous solution prepared by dissolving 50 grams of dextrose in enough water to make 1 liter of solution? Dextrose is a non-electrolyte, and the body temperature is 37.0 degrees Celsius. So in this case, we're solving for the osmotic pressure pi. And so we don't know that. Now, molarity, we need that. We don't know that one either. Okay, R, we do know that one. That's a constant, 0.0821 liter atmosphere over K mole. And the T, the temperature, we actually do know that one. That's 37.0 degrees Celsius. We need to convert that to Kelvin. If we convert that to Kelvin, it's 310 Kelvin. All right, so the only thing that we're really missing is that we need to know the molarity. Now, we do know how much dextrose we're using, 50 grams. So if we convert dextrose, the grams of dextrose, to mole, so the mole, if we find the molecular weight of dextrose, C6H12O6, the molecular weight should be 180 grams per 1 mole. So 50 divided by 180, and then if we convert this, if we add enough liquid, enough water to make 1 liter, we'll just do everything at once. The molarity should be 0.278 molar. So now we know what the molarity for the solution is. All right, so now we have enough that we can use our equation. So we've got pi is equal to the molarity times the universal gas constant times the temperature. The molarity is 0.278 molar. The universal gas constant is 0.0821 liter atmosphere over K mole. And the temperature is going to be 310 Kelvin. All right, so what's kind of nice is that everything should cancel out. Kelvin will cancel out with Kelvin. The moles will cancel out with the moles. The liter will cancel out with liter. So the only unit left is going to be atmospheres. So 0.278 times 0.0821 times 310 should give us 7.07 atmospheres. Now, the only thing is we've been dealing with atmospheres. We're dealing with atmospheres in this problem. We've been dealing with millimeters of mercury for everything else. If you wanted to convert from atmospheres to millimeters of mercury, okay, so if we have 7.07 atmospheres, remember that there are 760 millimeters of mercury in 1 atmosphere. Okay, so 7 times 760 should give us 5373.2 millimeters of mercury.